Now, what is this theory? Well, you're dealing with delayed feedback neurons. You just heard about Fokker-Planck. You just heard about noise. So you have to throw everything together with delays. I won't go into the details. It gets very technical. There's a few approaches out there. Some in the group of David and Carl and Nicolas Brunel and Vincent Hakim doing Fokker-Planck analysis in the mean field, and you can derive these kinds of oscillations that go through into the system as you change the parameters. We have another brand of theory. We start with integrating fire models. And the integrating fire models have their internal noise, and they have some external input. And then they have feedback. And this is the gain of the feedback. And where's the parameter C, which changes the spatial correlation? Well, it's a property of the input. So C is buried in there somewhere. C is in that input I. I'll show you specifically. The input I is this noise, and C is inside inside here. So what you need to do is to find out when this spikes, and you need to know how the spikes get modulated if there's noise coming onto the system. Now, there's a way to do this. If the system were perfectly linear, there's a way to do this called linear transfer function analysis. But neurons are not linear. They have thresholds. So you have to do a lot more work to get at the answer. Yeah?
So why J this is?
Why what?
Why J?
Oh, you're summing
Why?
Yj is the sum of the delta functions produced by everybody in the network. So Y1t is the sum of all the delta functions produced by neuron 1. So you have to sum over everybody because we're assuming global coupling. And this tells you the shape of the coupling. And that coupling encompasses both synaptic properties, the postsynaptic population, everything is lumped in there. We're not modeling the next population. We're just saying it's like a wire that comes back. But there's some kind of distribution of delays, and it's thrown in there. Okay, and this is the basic idea, but as I said, I don't have time to go into detail. You say, this is called linear response theory. So you say, here's the background firing. So the firing you see in your cell is a sum of two things. It's a background firing that's already there. And we know that. We know these cells are firing randomly when you're not doing anything to them. They're already firing away. So that firing, you take the Fourier transform, that's this term, background. But then you have to add whatever perturbs this firing. And that is going to be two quantities. The input to the cell times the response of the cell at that frequency. This is a quantity that's very difficult to calculate. Some people have done it, and we use it. And this is the quantity that's the input. Well, the input comes from two places. It's the input from the outside world and the input from the feedback. These are all the inputs to the cell. So you throw that in to the equations, you shake, and you come up with these expressions, okay, which have all the parameters that you need in there. This is the power spectrum of your spike train as a function of frequency. Here's the parameter C. Shows up right there. As you change C from 0 to 1, this term starts appearing. And this term is the gamma oscillation, is the resonance in the system that gets excited by the input. Here's the feedback gain, here's the delay, here's the synaptic time constant, everything is, you can just put stuff in there. Okay, and that's the answer. So this is one approach to understand delayed feedback with noise and how spatial input can modulate this. Okay, the spatial input is coming in right here, this term here. The power spectrum of the input times whatever you can call this, the transfer function or the susceptibility function or the Green's function, depending how you were brought up. Okay.
Sorry?
Yeah.
Does the delay determine the frequency that you come?
So yes, so you can go and plot the frequency. You'll see out of this expression you can get the resonance. And you'll see the delay is one of the main determinants of that frequency, of the gamma rhythm. Okay, so in this system, the feedback is important for gamma rhythms. I'm not saying that this is a general rule. We can get gamma rhythms for other reasons. But usually it's recurrent connectivity. Okay. Okay. So let's see. I was going to show you something else. Okay. Here's information transfer. So I can do input-output coherence for a delayed feedback network. Here's the idea. I want to measure this quantity, which is, I spoke about it yesterday in the context of plasticity. We want to see how linear the system is. If I send a 10 hertz wave into my system, does the response show perfect modulation at 10 hertz? That's the idea. If it does, the answer is 1. At 10 hertz, this would be 1. If it doesn't care at all about that frequency, the answer is 0. So this is a measure of the coherence. It's the cross spectrum, or the gain, divided by the spectrum of the input and the spectrum of the spectrum. Okay? So what we're going to look at is, generally, in neural nets, what happens when you put input with feedback. So the system here is a bit different. It's like the one we had before, integrate and fire, but it's not integrate and fire, it's perfect integrate and fire, which some people hate. They just want to leave the room as soon as they hear that word. Okay? But it can still get you quite a bit of mileage. Okay? You can redo all this with leaky integrate and fire if you want, but it doesn't matter. Okay? So you just have some perfect integrate and fire, some noise, some input, feedback 1, feedback 2. I have 2 feedbacks. One feedback is excitatory, the other one's inhibitory. It turns out that in this system, as in most parts of the brain, the feedback always comes in 2 varieties. It goes directly back with excitation, and it also makes a detour via an interneuron and comes back with inhibition. Okay? So there's always this kind of balance between excitation and inhibition. So the question is, what does this do from the point of view of information transfer in a very simplistic way? So you can simulate this thing. Turns out you can do theory on that. Nicolas Brunel figured out what the susceptibility function is for this perfect integrated fire and use this formula. And this is the kind of thing you get. So you have the coherence as a function of frequency. Again, between 0 and 1. The black line is when there is no feedback. This line, with the gray, is when there's only negative feedback, or inhibition. And this line with the triangles